Population inversion is the topic of today's discussion, and this topic is based only on the Maxwell-Boltzmann distribution law. So, what is the population inversion and what is the importance? So, we can write here. I'm saying Pi to the population inversion. So, what is Pi? And what is the importance of it here? The importance. So, what is the importance of population inversion in leisure? We will see it. And in general case, what is the situation? And in a special case, that is of the leisure. So, these are the two cases here. One is the general case and second is the special case. So I will focus all these points on these three. So let us see one by one. Maxwell-Boltzmann distribution law of atoms. Right. This says n is equal to n naught e raised power minus e upon kt, where n naught are the total number of the atoms. Here I have considered N1, N2, N3. Three energy states we have taken correspond to the E1, E2, E3, right? And these are the number of atoms into that states. And how one can find out those basically idea? You can find out by using this law. And in general, you have seen here N1 is greater than N2, greater than N3. And obviously E3 will be greater than E2. So how I can represent it? So the way to represent it, suppose this is E1 and this one is E2 and here you can say this is E3. So obviously E3 energy level is higher as compared to the E2 and so E1. Right, so you can say N1 are the number of atoms, N2 and N3. So N0 is equal to N1 plus N2 plus N3, right? So these are the total number of atoms. And so how this N1 number are distributed correspond to the energy E1, that is explained by this law, right? So now let us see further. If I have to present it in a graphical way, how I can show this? So on this axis I have taken the number of atoms and on this scale the energy. So this you can say here E1, this is E2 and this one is correspond to the E3, right? And now as you know that N1 are the number of atoms correspond to the E1 and in ground state N1 number of atoms which is larger than N2. So I can show it by this line right here. So this is correspond to the N1 and then after N2 are smaller as compared to the N1. So this is N2 and this is you can say N3. I'm taking tea, so don't mind please. Okay, so if you see this equation, n is equal to n naught e raised power minus e upon kt, this is exponential behavior, right? This number of atom distribution of these atoms show the exponential behavior. You can see here if I show you by this line this pink color. So if I start here initially, it means that when n is smaller, right? And so this behavior actually, if I join all the line, so this is in this way, and this behavior is exponential. So here this is A point, this is B point, this is C point, and this you can see through this equation, n is equal to n naught e raised power minus e kt. So a very small energy, number of atoms will be larger, and at very high energy, here you can see that a number of atoms in higher energy state will be smaller as compared to the lower energy state. So this is the idea, and this you can say in general. In general, what happens in any specimen? Smaller energy have larger number of atoms, higher energies have a smaller number of atoms. So now let us see the case of population inversion, which I have discussed earlier, and you have seen that this is the requirement. And population inversion is what that I can explain with the help of metastable state. So as you know that this is the ground state E1. This you can say E2 is metastable state, and this E3 is the excited state, right? And this is the ground state, this is the metastable state, and this is the excited state. You can say the lifetime of the excited state remains generally of this order, 10 to the power minus 8 seconds. This is the lifetime. And metastable state, this is metastable state, and its lifetime is around generally 10 to the power minus 5 seconds. Okay, and this is the ground state. What happens actually, as you know, the atoms are in ground state, and a specific frequency photons lies on it, and as a result, what happens, these atoms goes into the excited state by this way. You know the lifetime of this state, right? E3 is smaller, that is 10 to the power minus 8 seconds as compared to the E2. So during what happens when these atoms get excited and reach here, they will stay here up to the 10 to the power minus 8 seconds, and immediately after that time jump into this metastable state, right? And will stay here, right? And the lifetime of that is 10 to the power minus 5 seconds, longer, 1000 times longer as compared to the excited state. So during this process, as you know, the other atom get excited and goes into the excited state, and similarly same time during that process, these excited atoms are coming into the metastable state, and here they are basically accumulating. Why? Because the lifetime of this state is more as compared to the excited state. So all these atoms almost reach here in excited state and jumps into the metastable state, and now a situation basically occur where we observe more number atoms N2 in metastable state as compared to the ground state. If N3 is the number of atoms in the excited state. So this is the situation. Here N2 is greater than N1, and this situation you call population inversion. Right? This was the idea, and this is a special case where you observe that more number of atoms in excited state, right, as compared to this one lower state. And this state here I have mentioned as metastable state. So let us see the behavior of it as we have seen in the last slide. So if I have to draw the behavior of N and energy, what is that? You will observe here, this suppose E1, this is E2, and this is E3. Then now E1 is smaller, right, as compared to the E2. E3 is already small, right? And this is N1, and this is N2, and here this is N1. So this is a special case, you can say, and you observe it when population inversion achieved, right? And there is no exponential behavior right now because this is a special case. So here you can write E3 is greater than E2 greater than E1. There is no doubt, this is clear. But here in terms of the number of atoms in different energy states, and this is N3. Here N2 is greater than N1 and N1 is greater than N3, right? And this is the requirement for the stimulated emission, and from that we observe the laser light. So if you have any doubt related to this idea and the earlier one which we have written here, right, this one, you may get confused in this, but if you, right, if the idea is clear, then okay. But if you have any doubt, you can ask the question that why I have written in this way, or what is the reason of it, right? So here this is important point. So here N2 is greater than N1, still E2 is greater than E1. And earlier, the first situation in general case, E2 still is greater than E1, but N1 was greater than N2. So these are two cases. This is a special case and this is general case, right? So if you have any question or doubt, you can ask, right? Or you can suggest the topic, so, right, or you can like or subscribe the channel, other things, and don't forget to press the bell icon, right? I could not make it exactly, but this is bell, and you have to press it, right, to get the further notifications.